So folks, in this video here, we're going to look at an example of the method of variation parameters. I presented the theory in the last video, but I want to give a quick summary of our findings for that before we tackle the question on the next page. So the method of variation parameters, and we're doing it here for a second order ODE, assumes we've got an ODE of this form where notice that the coefficient functions in front of y prime and y are not necessarily constants. So in some examples this could be a 3 or a 2, but in other examples this might be the sine of t and t squared. And then the right hand side is not necessarily going to be 0, so it's not necessarily going to be a homogeneous equation. So what's our technique for finding the general solution? Well, the general solution we saw in the previous video is simply the solution to the corresponding homogeneous equation, that part should look familiar, plus the one particular solution. So all of that should look like stuff we've done. But what we learned is that we're going to give the particular solution in this form here, v1y1 plus v2y2. And we need to then simply solve for those v1s and v2s. And if you go back and you look at that video, we had a whole bunch of work, and we basically came up with a system of two equations. And as far as, because we are assuming we know y1 and y2, the solutions to the homogeneous equation, the unknowns are simply v1 prime and v2 prime. So we go ahead and solve this system of equations. Typically we do that using Cramer's rule. And then you simply integrate the v1 prime and the v2 prime to give you your v1 and v2, and then you plug all of that into the ODE. Folks, there's a couple of important notes here. The first one is certainly probably the most common mistake students make on a problem like this. All of this theory assumes that the coefficient function in front of y double prime is a 1. But sometimes you might be given a question where you have a coefficient function in front of y double prime that isn't 1. Well, never fear, just simply divide that coefficient function through on both sides. But then, of course, and this is what gets into our existence uniqueness theorems, you have to exclude any points where a2 of t is equal to 0 because of that process of dividing it through. Okay? And again, one more time, we typically solve that system. That's that system right up here. We solve this system using Cramer's rule, and so we can actually give v1 and v2 explicitly as a formula. And then one thing that I haven't mentioned yet, and it's not really a big deal, is that notice that this expression that shows up in the denominator here is simply the Wronskian of our two linearly independent solutions to the original homogeneous equation. So by the way, up here in your notes I've asked you, how do we know that determinant's non-zero? And the answer is because it's simply the Wronskian of the two linearly independent solutions to the differential equation. And when we're dealing with solutions to linear homogeneous equations, that Wronskian is either always 0 or never 0. And so that's why we know that we can go ahead and do that. So that was a really long introduction to this problem here. So go ahead and read question number 5, and let's think about what we want to do. So folks, I want to mention two interesting facts about this. I guess actually just one interesting fact about this differential equation here. Notice that in this case, unlike all of the other ones we've seen, the coefficient functions aren't necessarily all constant functions. I guess in this case, that 2, that's a constant coefficient function, but the other two are not. Okay. The other thing is that in this case, I guess we could have, if these had been constant coefficients, we could have used the method of variation of parameters, or excuse me, the method of undetermined coefficients on this, because it's a polynomial times a trig function. But you could have far more complicated functions here and still usually end up being able to use this procedure in the problems we encounter in this class. All right, the next thing is that normally what are our steps to solving this? And let's just go ahead and recap the steps. 1 is to solve t squared y double prime minus 2ty prime plus 2y, come on, equals 0, the corresponding homogeneous equation. Then 2, the second step is to find one particular solution. And 3, give the general solution as y of t equals yh plus yp. So the thing that the technique that we're learning here is that for the process of finding the particular solution, we're going to use this new method of variation of parameters. But notice that we still have to find the solution to the corresponding homogeneous equation here. And we cannot use the characteristic equation technique on this problem because I don't have constant coefficients here. So in this case, for me to make the problem moderately feasible for us to do, I had to tell you, and actually I stole this from another textbook, I had to give you the two solutions to the corresponding homogeneous equation. Okay, let's go ahead and first note that the general solution to the corresponding homogeneous equation is yh of t equals c1t plus c2t squared. And there's just a fine point that I need to make sure we make is just because I told you these were two solutions to the homogeneous equation doesn't mean they form the general solution. But we see that because they're Wronskian. The Wronskian of t and t squared, that is equal to, and you can compute this, and when you do so, you get t squared. And you can find at least one time value where that's non-zero. So, since, t equals 1, for instance, is a non-zero Wronskian, t and t squared are linearly independent. So just because I gave you these two solutions, it is important to note that they are linearly independent before you say that they give the general solution. Of course, you probably already knew that t and t squared were linearly independent. So now we just have sort of a plug and chug process left to find yp. So remember, our guess for yp is to say that yp of t would be some v1 of t, y1 of t, plus v2 of t, y2 of t. And then we just need to find v1 and v2 like we did in our theory video for this. I'm just going to go ahead and rewrite this as yp equals y1v1 plus y2v2. And remember that the way we're going to find the solution then is to simply go back to the previous page. We're going to solve the equation. So to find v1 and v2, first solve the system of equations. And there were two equations. The first one, and this one's maybe a little bit hard to remember, the first one is that y1 v1 prime plus y2 v2 prime has to equal 0. And the second equation that needs to be solved is that y1 prime v1 prime plus y2 prime v2 prime has to equal f of t. And if you're unsure of that, just go back and look at that's what we derived in the previous video, and here we have it in our summary. We're in the process of solving this system of equations right here. Okay. So in our case, y1 is t. And so y1 prime of t is just 1. And y2 of t is t squared. And so y2 of t, y2 prime of t is just 2t. And so I can go ahead and find v1 prime and v2 prime by Cramer's rule. So we get v1 prime is the determinant of, and here I'm going to go ahead and put these similar to how I did in the video, so hopefully the color coding will kind of ring a bell. So there was our f, and there was 0, so we'll put 0 and f here, but what is our function? That is the t sine of t. And folks, I have made a huge mistake. I guess not a mistake yet, but I haven't put this into the correct form yet. So we're going to go back to the original ODE. Let me make some space here. We'll put it in blue so we can see it. And the original ODE was t squared y double prime minus 2t y prime plus 2y equals t cubed of the sine of t. But the method of variation parameters won't work with this as my forcing function. I can't use that as the forcing function because the whole thing was developed assuming that the coefficient function right here was 1. So what I need to do, like I said in the in our notes at the beginning of this video, is divide everything through by the function in front of the y double prime term. So this gives me y double prime minus 2 over t y prime plus 2 over t squared y is equal to t sine of t. And here, because I'm dividing by t squared, that's assuming t does not equal 0. So any solution I find has to have an interval that doesn't contain 0 in it. Okay, so picking up, I guess I'm following the rule, Cramer's rule, and I replaced the first column of the determinant with 0 and then this function t sine of t. So that's why I had to pause and return to the original problem here, was how did we know that it was t sine of t? And the answer is because I had divided by t squared. And then we would have y2, which is t squared, and y2 prime, which is 2t, that determinant, divided by the original Wronskian, which was t1, t squared, 2t, and then we can go ahead and compute this. So if we compute these two determinants, notice the numerator would be minus t cubed sine of t. That's the determinant of that first determinant. And then that second determinant in the denominator there would be 2t squared minus t squared, which is just a t squared, which gives me minus t sine of t. So my v prime of t is equal to minus t sine of t, but I need to find v, so we're going to just simply integrate. So my v1 of t is simply the integral of minus t sine of t dt. And here, if you're rusty on integration by parts, you'll want to go back and review this. To save a little bit of time, I went ahead and computed it beforehand. So if you do this by integration by parts, you would end up with t cosine of t minus the sine of t. And you can verify that through differentiation if you want to check that. So that's our v1. And our v2, well, we want to find v2, but to do that first we have to find v2 prime, and we're going to follow that with Cramer's rule. And Cramer's rule said that that would be the first function times its, and then its derivative in the second entry. And then there's that 0 and that t sine of t in the second column, all over the original Wronskian. So if you've computed the Wronskian once, you could actually just go ahead and put t squared there without recopying this part. It doesn't really matter. But notice that gives me t squared sine of t all over the Wronskian of my coefficient functions, which are the Wronskian to my solutions to the homogeneous equation, my two linearly independent solutions. So we divide by t squared, and we get just the sine of t. Now careful, that's v2 prime. So v2 prime of t is equal to the sine of t. But that means that v2 of t is simply the integral of the sine of t dt, which is equal to minus the cosine of t. By the way, folks, there's a plus c here in both these cases, but of course what we do is we pick, so any choice of c would work, but it makes sense to pick c equal to 0 just to make our lives easier on us. So bear with me because we're almost done. I do want to emphasize, though, folks, that I have students, they get to this point, they learn the process of solving the two equations for v1 prime and v2 prime, so they're able to, they take these two equations here, they solve each of them with Cramer's rule, then they integrate and they find v1 and v2, and then they want to stop somehow. So let me just remind you that we said that our general solution is the corresponding homogeneous solution plus our particular solution, but our particular solution is v1y1 plus v2y2. So we still have a little bit of calculating left in this problem. And so yp, let's come over here and put it, yp, we said was v1y1 plus v2y2, but we just found that v1 was t cosine t minus sine of t, so t cosine t minus sine of t, times our y1, which is the function t, that was our first solution to the original homogeneous equation that we were given in the problem, plus our v2, which is we just found to be minus the cosine of t. That's our v2 times y sub 2 squared, y2 squared, y2, which was t squared, excuse me, folks. And so if we do some simplifying here, let's see here, this would give me a t squared cosine of t, but this would cancel with this minus t squared cosine of t. So the only term that remains is this minus t sine of t. So now we've given the particular solution to this ODE, and then the last thing that remains to be done is to give the general solution. So our y sub t is equal to c1t plus c2t squared plus negative t sine of t. I give it a straight mark there. And this was the solution to the corresponding homogeneous equation, and this was our particular solution. Of course, though, we have to add, because it's not apparent from this, we have to add for t not equal to 0. Why? Because at some point we divided by that t squared in order to do this whole method. So there we have the general solution to this second order non-homogeneous equation. The part where you might feel like we cheated is that I had to give us the two homogeneous solutions because we couldn't find them using the, calculate the roots to the characteristic equation process. That's a good place to stop, folks. We're going to pick up with this method, and we're going to do it for higher order linear ODEs in class and answer some more questions at that point. Let me know if you have any questions on this, folks, and I thank you for your participation.